Inside a mass spectrometer, identifying an unknown toxin begins with a violent reaction. The target molecule is shattered into dozens of charged fragment ions. These fragments don't emerge in orderly rows. They burst forward as a disorganized stream traveling at several kilometers per second. To identify the original chemical, every single fragment in that stream must be weighed and sorted with microsecond precision. A physical sieve cannot be used here. At these speeds, atomic fragments would simply crash into a physical grid, neutralize, or react unpredictably. The Quadrupole Mass Analyzer operates within these constraints by removing physical contact from the equation entirely. It creates a series of dynamically oscillating electromagnetic fields to catch and manipulate ion trajectories in midair. By relying purely on the speed of electromagnetism, the system sorts mass based on flight trajectory, turning a disorganized stream of atoms into a precise sequence of legible data. This blueprint shows the basic physical architecture of the analyzer: 4 high-precision metal rods, arranged perfectly parallel to one another. Because the resulting electromagnetic field must be uniform, these rods are machined to exact tolerances from materials like stainless steel, molybdenum, or gold-coated ceramic. The opposing pairs of rods are electrically connected. The top and bottom pair form the y-axis, while the left and right pair form the x-axis. To create the sorting field, the system applies 2 distinct types of voltage: a steady, static direct current offset and an oscillating radio frequency, or RF voltage. The y-axis, top and bottom rods, carry a positive DC bias, plus U, superimposed with an RF wave, plus V cosine omega t. The x-axis rods receive the opposite, a negative DC bias, minus U, with an RF wave 180 degrees out of phase. Layering a constant static pole with high-speed oscillating pushes creates a spatial trap where only particles of specific mass-to-charge ratios maintain a stable path. Looking at this side profile view of just the y-axis, the positive DC voltage creates a repulsive central potential. As positive ions enter the central gap, they are pushed away from the top and bottom rods. Heavy ions possess significant momentum, responding slowly to rapid field changes. They succumb to the steady positive DC pole whenever the rapid RF cycle dips negative, causing them to drift outward and collide with the rods. Light ions experience a different environment. Their low mass allows them to react almost instantly to fast RF oscillations. Even though the DC field tries pulling them off course, the high-frequency RF field continuously kicks them back toward the central axis, keeping their path bounded. By discarding massive fragments and allowing only light ones to pass, the positive y-axis functions mathematically as a high-pass mass filter. On the x-axis, the effect is inverted. A negative DC bias constantly attempts pulling positive ions outward toward a crash. Heavy ions are too slow to be saved by the RF voltage, drifting smoothly outward until they strike the rods and neutralize. Light ions fail here, overcorrected by the intense RF field until smashing into the rods. Ultimately, only a mid-range mass perfectly balances both forces, heavy enough to resist the violent RF kicks, but light enough to avoid the steady DC drift. By destroying light fragments and letting heavier ones pass, the negative x-axis functions as a low-pass mass filter. Only ions residing in a narrow mass window survive this intersecting gauntlet. When we combine these 2 perpendicular filters, the ion motion inside the complete 3D apparatus is governed by the Mathieu differential equation. This graph plots parameters A and Q, representing physical DC and RF voltages scaled against the ion's mass-to-charge ratio. If an ion's coordinate lands inside the triangular boundary, its trajectory remains stable, navigating the rod successfully. If outside, its oscillations grow exponentially until it crashes. Adjusting these voltages lets chemists plot coordinates inside this phase space, turning a 19th century abstract equation into a physical machine for trapping specific atoms. To identify a molecule, we cannot look at just one mass. We need to record the entire range of fragments produced during its destruction. This split view shows the standard scanning mechanism. The instrument rapidly ramps up both U and V voltages while keeping their ratio constant. As the triangle sweeps across the scan line, mass 58 achieves a stable trajectory, passing through to the detector. Milliseconds later, as the voltage continues to rise, mass 58 becomes unstable and crashes, clearing the path so a heavier fragment, like M by Z91, can stabilize and register its presence. By sweeping these voltages thousands of times per second, the quadrupole systematically reconstructs the full mass spectrum, the unique fragmentation fingerprint of the molecule. In cases requiring extreme sensitivity, such as detecting trace poisons, the instrument can focus all its attention on a single target. In selected ion monitoring, or SIM mode, the controller locks the U and V voltages to target one specific mass ratio continuously. By ignoring all other masses, the instrument can accumulate a much larger signal for its target, boosting detection sensitivity up to 100-fold. From entry to exit, the quadrupole handles thousands of fragments per second without a single moving mechanical part. Compact, robust, and mathematically precise, the Quadrupole Mass Analyzer proves that by mastering high-frequency electromagnetic fields, we can transform a chaotic stream of fragments into a clear mass spectrum, the definitive chemical signature of the world around us.